In this video, we'll be talking about the unit circle. It's a very important concept, and we want to build it up for you guys so you will truly understand it rather than memorizing it, because a lot of the students I work with, they just memorize the unit circle. They don't truly understand what the deep lessons are. And before watching this video, you really want to make sure you're sharp with sine, cosine, and tangent. You should be able to quickly solve any one of these right triangle problems in just one step, using sine, cosine, or tangent. And we will have some sine, cosine, and tangent calculations in this video, but I'm going to be going over them pretty quickly. The unit circle concept is really an extension. It extends your knowledge of sine, cosine, and tangent. So what we first start off with is the observation that you can take the sine, cosine, or tangent fraction of any angle of a right triangle. So you can take the sine, cosine, or tangent of a small angle of a right triangle, like 15 degrees, or of a big angle, like 60 degrees. But notice that the biggest angle of a right triangle that you can make is basically like 89 degrees. You can't have a right triangle that has an angle bigger than 90 degrees. That's why our lists basically stop at 89. So our sine, cosine, and tangent lists basically only exist for angles in between 0 and 90. Because if I try drawing a triangle with an angle bigger than 90 degrees, let's say 145, this triangle is not a right triangle anymore because it doesn't have a right angle. And we can only use sine, cosine, and tangent for angles of right triangles. So you think it would be impossible to do the sine, cosine, or tangent of 145 degrees. But if you actually put these into your calculator, you will get an answer, a number. You won't get a calculator error or something like this. So you can actually do the sine, cosine, and tangent of 145 degrees, and you can actually take the sine, cosine, and tangent of any angle. And that is the main takeaway from the concept known as the unit circle, in my opinion at least. It's the fact that you can do the sine, cosine, and tangent of any angle that you want. In this video, we're really going to build up that concept and explain what that means and why it's possible and how we use it. And to begin that conversation, we really have to introduce the idea of coordinate systems and what a coordinate system is. So a coordinate system is just a way to use numbers to say where things are in space. And the one that you've probably seen before is the Cartesian coordinate system, which uses x and y. And here we have a couple of points on our grid, and they're referred to using x and y, the Cartesian coordinate system. And what I really want to draw your attention to is that our first point there in quadrant 1, 5, 2, that 5 is the x-coordinate, and what that really means is the length of this line right here. Remember, you want to think about these points not as just two numbers, 5 and 2, but what those numbers represent. The x-coordinate, the 5, is that green line, and the y-coordinate, the 2, is really this length right here. So you want to start thinking like that. And of course, you want to remember what a quadrant is. Quadrants are just how we split up the coordinate system into fourths. We've got quadrant 1 here, 2 here, 3 here, and quadrant 4 in the bottom right. So the coordinate system you are probably not as familiar with is the polar coordinate system, which uses r and an angle, theta, to represent where a point is in space. And r, the first number, is the distance from the origin to the point. So this is r. And theta, of course, is the angle of the point as measured from the positive x-axis going counterclockwise. So our 26.56 is our theta here, our angle. And just as another example, check out that point in quadrant 2. Its r is 5, again it's this length here, and its angle is 143.13, and again, how you measure that theta, that angular position, is counterclockwise from the positive x-axis. And notice how this polar way of specifying where points are allows for some pretty big angles. I mean, here we are getting angles bigger than 90 degrees right here, and we can imagine that if we had a point in, who knows, quadrant 3, its angle would be very big. It would be bigger than 180 degrees. So right now we're seeing how it's beginning to be possible to have angles that are bigger than 90. Now here's where sine, cosine, and tangent come in. So there had to be a way to convert a point from its r theta form to its xy form. There had to be some mathematical equation to take a point given in polar and convert that same point just in its Cartesian description. And actually, the answer to that question is sine and cosine. We can look at this situation as a right triangle. This black point here, notice that its x-coordinate, like I was saying before, this x-coordinate is going to be this green length, and its y-coordinate is going to be this blue length. So this is a right triangle. And looking at our angle, our theta, as our angle of focus, that would make this x length the adjacent, so we'll call it the adjacent x, and this y length the opposite. So we'll call that the opposite y. So the y coordinate is the opposite, the x coordinate is the adjacent. Our r, that's our hypotenuse, and of course our angle theta, that's our angle of focus we've been talking about in the previous 3 videos. So we can use cosine of our 36.87 to basically calculate our x-coordinate, and sine of 36.87 to calculate the y-coordinate. And I'll put the math up here for that really quickly. So you can see how the cosine allows you to get our x-coordinate of that point, 4, and the sine, carrying that sine calculation out, allows you to get the y, the 3. And you can see from those grid lines that 4 and 3 are the correct Cartesian coordinates of this point. So people started thinking that the problem had been solved. There was now a straightforward mathematical way to convert a point in its polar form to that same point in Cartesian form. And it was to use cosine and sine. The x-coordinate would always be the adjacent of the right triangle, and the y would always be the opposite of the angle of focus of the right triangle. And this approach would work in quadrant 1, just like we illustrated here, but there was a bit of a hiccup in quadrant 2. And let's take a look at that. So we have a bit of a problem here. We can't make a nice right triangle using the angle of 121, as we discussed in the beginning. And since we can't make a right triangle out of this 121 degree angle, how are we supposed to use cosine and sine? So that was a bit of a problem. If we look at this, we realize that the x-coordinate is this length right here, the y-coordinate is this length right here, and that's looking like a right triangle. But the angle of focus of this right triangle will be that one right there, 180 minus 121, 59 degrees. The opposite of this right triangle is our y, and the adjacent of a right triangle is our x. Okay, so now we have this sort of cosine and sine approach set up. It's just that we're not using 121 degrees to do this. We're using this 59-degree angle of focus right triangle to do this. Alright, so now we'll do our cosine to find the x and our sine to find our y. So once again, we use the cosine to find the x and the sine to find the y. But if you look at it, the correct xy coordinates in this case should be negative 3 for the x and a positive 5 for the y. Looks like we got the positive 5 for the y, but look, our math got us a positive 3 for the x, when it really should have been a negative 3. So we are running into big problems when we try to convert a point in quadrant 2 from its polar form to its Cartesian form. First, we couldn't even use the theta, the 121. We had to recognize that the adjacent x here and the opposite y here formed a different right triangle, a right triangle based off of this 59-degree angle here. And then, even when we carried on with this 59-degree angle and crunched the cosine and sine of it, we were getting an incorrect x-coordinate. So there were a lot of problems here. So here's what the solution was. People still wanted to use this approach to convert from r theta to x and y. They wanted to do this in the simplest way possible. They just wanted to dump in 121 degrees and get out the correct x and y's. They didn't want to have to, find this 59, and then they definitely didn't want to have to plop the negative or positive on it manually. They just wanted the math to do it for them. So, what mathematicians decided was that the best thing to do was just to create a new cosine and sine entry in the sine, cosine, and tangent tables that we've been working with. Remember, those tables only had sine, cosine, and tangent for angles from 0 to basically 90, but now people realized that there needed to be some new entries. Here we were going to add two new entries here, the cosine of 121 and the sine of 121. And the reason these new entries were being added was so that we could convert basically a point from polar form to Cartesian form. So here's what was said about this. The cosine of 121 would equal 0.515, just like the cosine of 59 was, because remember, that the cosine of 59 allowed us to almost get it completely right. It got us the 3, but it didn't get us the correct sign. It didn't get us the correct plus or minus. So the cosine of 121 degrees would equal a negative 0.515. And another way of looking at why it's a negative is, imagine putting in 121 in here. Notice that the x will be a negative number and the r will be a positive number. And just a quick note here, the r, the hypotenuse, in all cases will always be a positive number. And the reason behind this is more of a physics, a vector question, so take a look at the vector video series if you want a solid answer to that question. So cosine of theta is equal to x over r, and sine of theta is equal to y over r. And because the x of an angle of 121 will equal some negative number, and the r will equal a positive number, and of course a negative divided by positive is going to equal a negative, the cosine of 121 shouldn't equal a positive 0.515, it should equal a negative 0.515. This is how we reason through this. Now let's do the sine. Now the first step is saying that the sine of 121 will equal the same thing as the sine of 59, because the sine of 59 basically got us that correct 5. But we have to be careful. Did it give us the correct sine? And in this case, yes it did. So the sine of 121 will equal positive 0.857. Exactly like the sine of 59. And again, you can also look at it in this way. Think about a point that has an angular location of 121 degrees. The y-coordinate of that point here will definitely be a positive y. And of course, like I mentioned, the r will always be positive. So a positive number divided by another positive number is just another positive number. That's why the sine of 121 will equal a positive 0.857. You can do the same for tangent too. Of course, 121 will have a tangent fraction. So the tangent of any angle is just the opposite over the adjacent of that angle. So in the context of this conversation about converting polar to Cartesian, tangent of an angle is just the y, the opposite, over the x, the adjacent. So the tangent of 121 degrees will equal the same thing as the tangent of 59, which is 1.66. But now we have to think about whether it's going to be a positive 1.66 or a negative 0.166. So again, we got to imagine thinking about a point that has an angle of 121 degrees, just like this guy right here. Its y, its opposite, will be positive. Its x, its adjacent, will definitely be negative. Positive divided by negative is definitely a negative number. That's why the tangent of 121 is a negative 1.66. So now, if you wanted to try the problem again, the problem of converting this point right here from its polar form to its Cartesian form, you could just use the cosine and sine of 121. So you could just run those cosine and sine calculations again. Of course, your calculator knows what the cosine and sine of 121 is, and you would just get -3 and 5 with, minimal effort. You wouldn't have to, find out this 59, and of course you wouldn't have to manually put the positive or negative about it. You wouldn't have to think hard. You would just use the cosine and sine of 121 and these equations right here. The cosine would give you the x, and the sine would give you the y. But of course, you want to definitely know why the cosine of 121 is the same as the cosine of 59 and has a negative on it. And you want to know why the sine of 121 is the same as the sine of 59 but has a plus sign on it. You want to know sort of the inner workings of this math. And that procedure, the steps that we just went through, is how we do that. How we determine the cosine, sine, and tangent of any angle. Even though the calculator, of course, has all those numbers for you, you want to know why, the reason behind it. Because again, this is the main lesson of the unit circle. So let's go through this procedure one more time, a little more faster this time, just so you guys sort of really pay attention to how we just did what we just did, so we can write some concrete steps in how to find the sine, cosine, and tangent of any angle. So, let's think back. What was the first thing we did? Well, we recognized that right triangle that was going to help us find the x and y of this point wasn't a 121 degrees. It was this right triangle here. It was that 59 degree right triangle. This is the triangle that helped us sort of split the point into its y and x. It wasn't a 121 degree right triangle, it was this 59 degree angle of focus right triangle. So this helper triangle is known as the reference triangle. So that was the first step right there. So that's our step one. We've got to find the right triangle that will help you split the point into its x and y coordinates, and that's known as the reference triangle. And you also want to be careful. Some people, they look at the situation and then think, okay, here's my reference triangle right here, with this being my angle of focus. Well, we got to be careful here. The adjacent of this angle of focus is the y, and the opposite is the x. Remember, that's not what we're going for here. The correct reference triangle has an adjacent, that's the x, and the opposite as the y. So again, that right triangle would be this one right here. The angle of focus would be right here, which makes This are adjacent, which is the x, and this are opposite, which is the y. So this is our correct reference triangle. Okay, so what did we do after that? Well, we used this 59-degree triangle to find the x and the y. We used the cosine of 59 and the sine of 59 to find the x and the y. So we know that the cosine of 121 should equal the cosine of 59, or at least just the number, the numerical portion of it. Remember, the plus or minus we had to sort of determine ourselves. So the cosine of 121 should equal 0.515, or at least just the number portion. Now we have to put on the plus or minus manually. We have to recognize that the x of our 121 will be negative and our r will be positive, and a negative divided by a positive will equal a negative. So the cosine of 121 is a negative 0.515. And we follow this exact same procedure for sine and tangent. So that's your step 2. Let's read through that. The sine and cosine of the angle, our 121 that is, will be equal to the sine and cosine of the angle of focus of the reference triangle. That's our 59. That's what we just did. Cosine of the angle that we're interested in, the 121, will equal the cosine of our 59, but we have to put the positive or negative on it depending on whether that x, that adjacent, and that y, that opposite, is positive or negative. We got to take a look at that manually. So let's just read through this statement one more time for the sine. The sine of the angle that we're interested in, that's the sine of 121, will equal the sine of the angle of focus of a right triangle. That's the sine of 59. Because the sine of 59, remember the work that we did in the beginning, the sine of 59 allowed us to figure out that exact y length. It's just we may have to put the positive or negative on it. So the sine of 121 will equal the sine of 59. That's 0.857. But now we have to put the plus or minus on it. And we know that the y of a point with an angle of 121, the y will be positive, the r will always be positive, so therefore the sine of 121 will equal positive 0.857. And of course we would do the same for the tangent. So that's how you do it. These two steps allow you to find the sine, cosine, and tangent of any angle that you want. And the reason why we need sine, cosine, and tangent for any angle is so that we can convert a point from its r theta form to its xy form using these equations right here. This is, in my opinion, the most important lesson of the unit circle. I know we didn't take a look at that circular diagram thing that we showed in the beginning, but knowing that diagram in your college engineering classes is not as important, not even as close to being as important as knowing why the cosine and sines of some angles are negative and, why they're this and why they're that. It's not as important as knowing these steps here and why they're needed. So this video is already pretty long, so we'll call it right here. I'll have a separate practice video so you guys can get some practice calculating the sine, cosine, and tangent of different angles.